Students, good morning. Good morning, everyone. In the last class, in atomic structure chapter, we already discussed great concept black body radiation. Black body, a perfect absorber and a perfect emitter. Now, students, just depends on the graph what we brought in my last class between intensity and wavelength. Max Planck noticed some important postulates with respect to that graph, and finally he is coming to his greatest quantum theory, and simply what we call Max Planck's quantum theory. Very important one, dear students. Now, let me coming to the major postulates of Planck's quantum theory, which is proposed by Mr. Planck in the 19th century. Now, let me write the major postulates in Max Planck's quantum theory. The first one is, dear students, the emission or absorption of energy is mainly due to, dear students, vibration of charged particles. Are you got it? Vibration of charged particles. Charged particles, nothing but atoms. Electrons also charged particles. And while we coming to students, the second one, the emission or absorption of energy radiation is a discontinuous phenomenon, and moreover in the form of, dear students, a small energy packets, and simply what we call quantum or quanta. So these are the two important assumptions which made by Mr. Planck. First of all, let us consider an atom. How atom absorb energy and emitted energy. What is the reason behind that, sir? Dear students, now let me explain. Let us consider a black body in which number of atoms are there. Okay, we just look at, this is the nucleus in which electrons are present in each and every shell. Keep in mind. So why emission or absorption of energy takes place, sir? This is mainly due to vibration of charged particles. Means, dear students, whenever vibration takes place in a solid material and these vibrations impart energy differences inside the atom. Means, some electrons move from lower level to higher level. Okay, and this is happens whenever energy is absorbed. And some electrons may fall down from higher level to lower level. And this is happens by the emission of energy. So, dear students, in every body, why emission or absorption of energy takes place, or the main reason behind that, due to the vibration of charged particles like electrons inside the atom, they may jump from lower level to higher level or higher level to lower level. If that atom absorb energy, then electrons take some energy and they move from lower level to higher level. They are not stable there, because higher level means higher energy. Higher energy means least stable. Okay, so here this is not at all stable. It again comes back to ground state. While it comes back to ground state from higher level, obviously it will release some amount of energy. So dear students, according to Max Planck, the emission or absorption of energy is mainly due to vibration of charged particles inside the atom. Students, and while we come to the second point, the emission or absorption of energy radiation is a discontinuous phenomenon, and moreover, it happens in the form of small energy packets called quantum. Now, let me explain that point. Before I am going to explain that point, dear students, I just take a small example. Okay. Students, just look. Two persons are there. Okay. This is person A and this is person B. Two persons are there. Two persons are ready to fight together. Okay, na? Iddar madhya manchi fight jarugutundi anukunnam. Are you interested for fights, ma'am? Are you interested to watch the fights? Okay, I am so much interested when I was side. Okay, so we just look at a strong war is happened between person A and person B. Just look at how it is going on. Students, first of all, person A took a water pipe and just throw a stream of water on person B. Okay, and B already took a bag of small stones. Just look at that, small stones. And now B starts throw these stones upon person A, one by one. Just look at that. This is the way how a war takes place between these two personalities, A and B. Sir, we are ready to explain Planck's quantum theory, but what about this is, sir? Is this a WWF game? Okay, students, while we come into these two personalities, we just look at that these two personalities just transmitted their energies during the quarrel. Just transmitted energies. Is it clear? But when we look at the person A, according to me, person A is Mr. Maxwell. Are you remember Maxwell? While I am discussing about Huygens wave theory of light. Are you remember? Yes, absolutely. Maxwell completely belongs to classical physics. Okay. Who strongly believes wave theory of light. And that's why Mr. Maxwell transmitted his energy in the form of a continuous manner. Yes, students, a continuous manner. Keep in mind. Okay, so that is Mr. Maxwell. So according to Maxwell, energy emission takes place in a continuous manner like stream of water. Oh guys, now we are coming to person B. Sir, who is person B, sir? Hey, he is Mr. Max Planck. Dear students, he is Mr. Max Planck. Max Planck is also ready to transmit his energy, but not in a continuous manner, dear students, in a discontinuous manner. Just look at what is going on, discontinuous manner. And he just thrown out the small stones one by one, not a continuous, it is a discontinuous. And he has a bunch of stones, students, and each stone is a small energy packet. Yes, students, each stone is a small energy packet. And the small energy packet is simply called as, dear students, quantum. Keep in mind. Have you got it? So that is the difference between wave theory of light and Planck's quantum theory, dear students. And each energy packet what Mr. Planck named quantum, and that's why this theory is simply called Max Planck's quantum theory, dear students. And that's why according to Max Planck, dear students, according to Max Planck, the emission or absorption of energy radiation happens in a body. Just imagine, of course, a black body. Okay. It is always a discontinuous phenomenon and not in the form of continuous matter. And moreover, this discontinuous phenomena happens in the form of small energy packets called quantum. Is it clear, students? But students, while we coming to third one, dear students, and these small energy packets, please observe that one, that what we call quantum, okay, propagate, underline the word, propagate in the form of waves, propagate in the form of waves. Confuse. Now I am here to solve your confusion. Okay, students, just look at that. What actually Mr. Maxwell believes that this is a body. Okay, some light is already absorbed by this body. Just imagine that is a black body, and we just heated it now. So total absorbed radiations are emitted out. So according to Huygens, this emission takes place in the form of a continuous waveform. Are you got it? A continuous waveform. Is it clear? This is according to Maxwell, which strongly believes Huygens wave theory of light. But students, according to Mr. Max Planck, the emission takes place in the form of small energy packets. In the form of small energy packets. Just look at that. That is Planck's theory. But what Max Planck strictly says that the emission of energy radiation takes place in the form of small energy packets, and moreover, they propagate in the form of waves. Means what, sir? Means, now let me explain. Let me explain. Small energy packets. Small energy packets. Propagates like a wave. Propagates like a wave. And this is what we call, dear students, Planck's quantum theory. And that's why, dear students, Max Planck is the first man who strongly believes that light not only has particle nature, light not only has wave nature, light has dual nature. Dear students, Mr. Max Planck is the first man who believes that light has dual nature. So, the emission of energy radiations takes place from a black body happens in the form of small energy packets, what we call quanta. But they propagate in the form of waves, dear students. And this is what we call Mr. Max Planck's quantum theory. Is it clear, students? Are you got it? Okay. Students, and now let me come into some important postulates in Max Planck's quantum theory. The emitted, dear students, the emitted energy of radiation, keep in mind always, is directly, dear students, proportional to frequency of that emitted radiation. Very, very important one. Are you got it? Means the energy of the emitted radiation is always directly proportional to frequency of that emitted radiation, dear students. Students, here we strongly believe that one thing, sir, ఒకవేళ మ్యాక్స్ ప్లాంక్ చెప్పినట్టు స్మాల్ ఎనర్జీ ప్యాకెట్స్ రూపంలో, పార్టికల్స్ రూపంలో గనక ఎమిషన్ ఆఫ్ ఎనర్జీ జరిగితే అసలు వేవ్ నేచరే లేదు కదా మరి అక్కడ. మనం ఫ్రీక్వెన్సీ అనే ప్రాపర్టీని ఎలా ఇంట్రడ్యూస్ చేస్తాము సార్? బికాస్ ఫ్రీక్వెన్సీ ఈజ్ ఏ క్యారెక్టరిస్టిక్ ప్రాపర్టీ ఆఫ్ వేవ్ బట్ నాట్ ఏ పార్టికల్. Are you got it? And that's why Mr. Planck gives a clear information. The emission of energy takes place in the form of small energy packets like particle nature, but however they propagate in the form of waves. They propagate in the form of waves, and that's why the energy emission is always directly related to frequency of that emitted radiation, which propagate in a wave form. Students, which propagate in a wave form, dear students, and that's why E is directly proportional to nu. But students, while we remove proportionality constant, we remove a new constant here. We introduce a new constant here, and that's what we call H along with nu. Sir, what is H sir here? Dear students, here H is simply called Planck's constant, and we know its a value, dear students, 6.625 into 10 power minus 27 erg into second, or if you want to write in joules, 6.625 into 10 power minus 34 joule into second. And this is the another important assumption which made by Mr. Planck. Keep in mind always. And moreover, students, here the emission of energy, the emission of radiant energy is always an integral multiply of a fixed amount of energy, dear students, called quantum, or simply quantum. Means the emission of energy E is always an integer multiply, means n into some fixed amount of energy, and energy of each packet what we call H in nu, dear students. Is it clear? What is n for here, dear students? Here n is simply an integer, dear students. N is an integer. Okay, 1 2 3 4 5 6 like that. Okay, now means, dear students, 1 H in nu, 2 H in nu, 3 H in nu, like that. Keep in mind. This is the another important postulate what we discuss with respect to Max Planck's quantum theory. Okay, then what Mr. Huygens strongly believes that, suppose emission of radiation takes place in the wave form, the total energy is 1000 joules. 1000 joules energy is emitted out according to Maxwell. But what Mr. Planck gives a clear information, you know. Yes, I agree with you. Total 1000 joules energy is released, but 1000 joules energy is released not in the form of continuous wave. It is in the form of discontinuous manner through energy of small packets. Keep in mind. If each energy of one packet is, just imagine 1 joule, there are total 1000 packets are emitted out, means obviously total energy once again 1000 into 1 joule, 1000 joules, Mr. Maxwell. This is the explanation given by Mr. Planck. Dear students, very important one. And that's why, students, according to Max Planck, the emitted radiation energy is always quantized and having its value E is equal to NH nu. Students, From our lower classes, we are somewhat feel difficult to look at that word quantize. ఎందుకంటే మన బోర్ అటామిక్ మోడల్లో కూడా అరే రిమెంబర్ బోర్ అటామిక్ మోడల్ ఓకేనా, ద యాంగులర్ మొమెంటమ్ ఆఫ్ ఎలక్ట్రాన్ ఈజ్ క్వాంటైజ్డ్ అని చదువుతాం. సార్ వాట్ ఈస్ ద వర్డ్ మెన్ బై క్వాంటైజ్డ్? సార్ క్వాంటైజేషన్ అంటే ఏంటి? నాకు ఇప్పటికీ క్లారిటీ లేదు సార్ క్వాంటైజేషన్ అంటే. స్టూడెంట్స్ ఐఎమ్ హియర్ టు ఎక్స్ప్లెయిన్ టు quantization. Okay, sir, what is quantization, sir? To well understood quantization, dear students, we just took potato, aloo. Okay, we love aloo. When I was said I'm interested to eat every day potato fry. Okay, so students, this is potato. Just imagine, and whenever we make cut into pieces and just fry, we get what, sir? We get a small chips. That's what we call potato chips. Dear students, potato chips. Sir, what it is? What is quantization? Hey, wait man. So students, a huge amount of starch inside the potato is subdivided into some equal parts in a discontinuous manner, and each and every chip has some fixed amount of starch, and that's the phenomena what is going on, quantization, dear students. So total energy, dear students, total energy is further subdivided into a small energy packets. Every energy packet is associated with, dear students, associated with some fixed amount of energy. Keep in mind, some fixed amount of energy, and that is the process what we call quantization, dear students. So according to Max Planck, the emitted radiation energy is always quantized, and its value is absolutely equals to E is equal to NH nu, dear students. And this is, students, what we call Mr. Max Planck's quantum theory. Very, very important one. And students, now let me coming to Einstein's approach towards Planck's quantum theory. Einstein ఎలా approach అయ్యాడు సార్ Planck's quantum theory మీద? Dear students, Einstein extended Mr. Max Planck's quantum theory, dear students, for all, keep in mind, for all electromagnetic radiations. For all electromagnetic radiations, Planck's quantum theory is extended by Mr. Einstein. The only difference is, in Planck's quantum theory, that small energy packet, what we call, that is quantum. I think it is, say some. But students, in case of light, okay, in case of light, okay, and that small energy packet, we simply call it as photon. That is the only difference. One quantum, nothing but one photon in case of light. But this Planck's quantum theory is extended to all electromagnetic radiations: gamma rays, X-rays, UV rays, IR rays, visible rays. That's what I'm saying, light. Okay, and also microwaves, etc., etc., etc. But here the replacement is one quantum. That word is just replaced with one photon, dear students. Okay now, and moreover, according to Einstein, dear students, the emission of energy takes place, just look at what is going on, takes place in the form of photons. Okay now, photons రూపంలో ఆ ఎనర్జీ ఎమిషన్ జరుగుతుందంటాడు మిస్టర్ Einstein, dear students. This is what we call simply Einstein approach. So, what we committed to, total energy E is absolutely equals to N into H into mu. What is N star here? Dear students, here N is nothing but number of photons. Keep in mind, number of photons. And this formula further extended, dear students. We just look at how that formula further extended. Now let me give an idea. So E is equal to N into H into, sir, what is frequency, sir? Mu. We know very well, man, C by lambda. Keep in mind. And that's why in the place of mu, we are substitute C by lambda. And that's why the emitted energy E is equal to N into H into C by lambda. Dear students, very, very important. And further, students, we know what is wave number. Are you remember? Wave number nu bar is equal to 1 by lambda. And that's why energy E is equal to N into H into C into nu bar. Because 1 by lambda is nothing but nu bar. Keep in mind. So these are the different formulas. We have to calculate what is the total radiant energy emitted out from a substance. Very, very important one, dear students. These formulas in examination point of view, keep in mind. And students, now let me come into the energy of emitted radiation formulas in objective point of view, very, very important one. And now we are ready to calculate the energy in the units electron volts. Very, very important one. Before I am going to explain that one, dear students, 1 electron volts means what you know, 1.602 into 10 power minus 19 joules. Keep in mind. Okay, students, we have formula actually energy E is equal to hc by lambda. This is Planck's quantum theory formula what we get, because E is equal to h nu actually. Says or no? Nu means what, sir? Nu means C by lambda. So hc by lambda. Okay. So if we substitute h value here, which is 6.625 into 10 power minus 34 joule second, and velocity of light 3 into 10 power 8 meters per second by wavelength, dear students, lambda. So here second cancel, and we just replace this relation. 1 electron volt is equal to 10 power, 1.602 into 10 power minus 19 joules. Then we get energy of emitted radiation in electron volts. We have formula simply 1242 by lambda. If we substitute lambda in nanometers, or simply 12420 by lambda. If we substitute lambda in angstroms, dear students. Most important one, just look at this relation, that's enough. And that relation is enough to bring this value. We know calculations very well. We just divided with the 1.602 into 10 power minus 19, that's enough. What is nanometers are, dear students? We already know 1 nanometer means 10 power minus 9 meters. What is angstroms are, dear students? 1 angstrom means 10 power minus 10 meters. So these are important formulas in objective point of view. And in tomorrow class, I am ready to explain some important problems in this Max Planck's quantum theory, which is a very, very important in examination point of view, particularly in objective point of view, dear students. Okay, and students, if you are really interested, I prefer Singe's book for physical chemistry, Singe's. Okay, very, very important book, Singe's. Okay na? So book ఎవరైనా కనుక మీరు తీసుకుంటే నేను చెప్తున్నటువంటి అంశాలకు సంబంధించి ప్రాబ్లమ్స్ అన్నీ కూడా మీరు ఈ బుక్లో చేసే అవకాశం ఉంటుంది. ఫిజికల్ కెమిస్ట్రీ, ఓకే, ఫిజికల్ కెమిస్ట్రీ బుక్ సింగిల్స్, ఓకేనా? మీకు ఎవరికైనా అందుబాటులో ఉంటే తీసుకోండి. స్టూడెంట్స్, and this is today my class. I'm so much excited what comments we have to be placed in my last video. Okay, now I'm so happy because black body radiation is a good concept. Okay, and that gave me somewhat boost of energy to give this today class, Max Planck's quantum theory, with somewhat better examples what I made. Okay, now నాకు తెలిసినంతగా నాకు తెలిసిన దాంట్లో కొన్ని మంచి ఎగ్జాంపుల్స్తో మీ క్లాస్ చెప్పారని నాకు అనిపిస్తుంది. ఓకేనా? ఇఫ్ యూఆర్ సాటిస్ఫైడ్ అన్న జస్ట్ మేడ్ ఏ స్మాల్ కామెంట్, ఓకే, విచ్ ఫర్దర్ గివ్స్ బూస్ట్ అప్ టు మీ. Students, thank you each and everyone. In next class we are ready to solve some important problems. Thank you students, thank you each and everyone. Bye.